Hello everyone and welcome. In this video we will start learning the meter module inside the Test Universe software in a detailed and practical way. This video is designed not only to explain the software setting but also to help you understand why the settings are important during the real meter testing application. So simply you can open the Test Universe software from here and you can navigate to the test modules and tools as you can see. Then you will find here the meter module, which is designed for manual or automated testing of energy meter. So simply the CMC test set will provide the inputs for the meter pulses and allows for a closed loop testing using optical scanning heads available as accessory. Also you can add it as a favorite from here, so it will be displayed in your favorite modules as you can see from here. Then you can click the meter module to open it, or simply you can add it into the OCC file from here by using the insert tab. Then you can insert the test modules, navigate for the meter module, and then you can simply click OK if you are creating a new module, or you can create it from a file if you have a saved once. So let us get back again to the meter module. So as you can see, we will follow the OMICRON Ohm's law and we will go step by step through the meter test object setting. In the beginning, we will explain the purpose of each parameters, how it affects the test, and what is the operator should pay attention to during the configuration. So let us open it from here by clicking the test object. Then you will find here the review file of the meter. By double click, you will see all the meter parameters. So the meter test object section is one of the most important parts of the meter module because it defines the identity and behavior of the meter under test, and also most calculation function inside the meter module depend directly on the setting and configured here. So before starting any actual testing, this section should always be configured carefully and verified properly. Now let's start with the first parameter. So as you can see from the meter type here, we have different meter types. This is where we tell the meter module what kind of meter we are testing. The software supports several meter types such as watt-hour meters, reactive hour meters, also volt-ampere meters, ampere-hour meters, and multifunctional meters. This selection is extremely important because it changes how the meter module performs calculation internally. For example, the watt-hour meter here measures active energy, while hour meter measures the reactive energy. Because of these differences, the software must know exactly what type of quantity should be generated. Also, some functions inside the meter module only become available when specific meter types are selected. For example, when a multifunctional meter is selected from here, the measure the quantity section later becomes available in the setting tab, allowing us to test multiple quantities separately. Also, we have here the Q-hour meter, which is a regular watt-hour meter that's installed with the potential circuit wired one phase behind the standard watt-hour connections, which means lagging the watt-hour connection by 60 degrees. This means this type of meter measures the quantity that's obtained by effectively lagging the applied voltage to watt-hour meter by 60 degrees. The quantity measured by Q-hour meter is called Q, and Q here is one of the quantities used in calculating the per-hour power. And please note that also the testing of Q-hour meter in a single phase mode is not possible. Then we have here the 4-wire meter and 3-wire meter. So we can define whether the meter is a 4-wire meter or a 3-wire meter, and this setting defines the electrical connection type of the meter. A 4-wire meter usually works in a system with a neutral connection, while a 3-wire meter is commonly used in a system without neutral. The meter modules also uses this information to generate the correct voltage system and phase relationship, and if a wrong configuration is selected here, the generated voltage and current may not match the real meter connection, which can lead to incorrect test results even if the meter itself is healthy. So during setup, it's always important to compare the software configuration with the actual meter wiring program. Then we have here a single phase box. So if the meter under test is a single phase meter, we simply enable the single phase option here. So once this option is activated, the meter module automatically changes the operation from a polyphase mode to a single phase mode. This means only one phase will be used during the test, and several settings related to a 3-phase operation will automatically become unavailable. So in practical applications, this option is commonly used for residential single phase energy meters. Then we have here exporting is 0 and exporting is 180 degrees. So this is the next setting to differentiate between exporting is 0 and exporting is 180 degrees. So this setting defines how exporting power flow should be viewed by the software. Exporting is 0 means that the exporting direction is viewed from the generator side, and this is the default behavior inside the meter module, while the exporting is 180 degree here means exporting is viewed from the consumer side. This may sound like a small detail, but it becomes very important when testing a bidirectional meter or a meter used in renewable energy applications such as solar system, and this selected option affects the direction of power flow used internally by the software during calculation and evaluation. Then we have here the gated mechanism test. So this feature is mainly used for electronic meters that use data register. Unlike normal pulse-based testing, these meters often require a controlled startup sequence before the actual measurement begins. So when gated mechanism test is enabled, the meter module first applies current for a startup period in order to stabilize the meter operation. After stabilization, manual start and stop pulses are used to initiate the test and reset the meter register. So the software guides the operator through the complete procedure using a dialog box and messages. Then we have the energy direction. So if you can see, this setting defines the operation direction of the meter. The available options are importing or exporting or bidirectional. So importing here means the meter measures the energy flowing into the load. Exporting means the meter measures the energy flowing back towards the source. And bidirectional means the meter can be or can measure energy flow in both directions. So this setting is especially important for modern smart meters and renewable energy application where energy may flow in multiple or bidirectional. Then we have the quadrant selection. So for the apparent power meter, the meter module also allows a quadrant selection. We can select quadrant 1 or 2 or 3 or 4 or all quadrant, and this box only active in case you have volt ampere hour meter type. As you can see from here, here is the volt ampere hour. Then you can see here the quadrant in first, second, third, and fourth or all. So you can press the help button and you can navigate to the test view, for example, just to give you overview about this setting. So here is the phase offset between the current and voltage depending on the power factor group, and here we have the fourth quadrant, and this is called the PQ plan for the active and reactive power and the apparent power as well. So also it can be considered for different types of loads if it's capacitive or inductive. So the quadrants here are used to describe different combination of active and reactive power flow directions. This becomes important when testing meters under different load conditions such as inductive or capacitive loads, importing power or exporting power. Then we have the pulse type setting defines the electrical behavior of the pulse output signal coming from the meter. The available options are active high or active low. Active high means when LED is active, a pulse will be counted. Active low, the pulse will be counted when the LED is inactive. So this setting must match the actual pulse output characteristic of the meter, and if the wrong pulse type is selected, the meter module may fail to detect pulses correctly, which will affect pulse counting and the final error calculations. Then we have the certified box. It's a user-defined box. So it's used to enter the calibration information related to the meter under test. Usually this includes the latest calibration date, the calibration certificate number. And since this is a user-defined field, additional notes or identification information may also be entered if needed. So this information later appears in the generated test report and help maintain proper documentation. Then we have the maximum creep time parameter is used during the creep testing, and this setting defines the maximum allowed duration for the creep test before the software decides whether the meter has started moving or not. So this value is entered as a percentage of the nominal time. As you can see, it's 120 or 125 can be used in this field. So the meter module allows the creep test to continue for up to 120% of the expected nominal rotation time. And the additional margin helps for slow meter movement during a low current creep conditions, and this nominal time itself is based on the meter constant and the injected energy. Then here we have the meter constant. So the meter constant here defines the relationship between the energy and the pulse output. So in simple words, it tells the software how much energy is represented by each pulse generated by the meter. And depending on the meter design, this value may be entered as a pulse per kilowatt hour or as a kilowatt hour per pulse, as you can see from here. And the meter module continuously uses this value during almost every calculation. For example, when the meter generates pulses during the test, the software uses the meter constant to convert those pulses into energy values. The same constant is also used to calculate the expected test duration, the nominal energy values, the actual energy values, and the final percentage error. So because this parameter is involved in many calculations, and incorrect meter constant will immediately affect the entire test results. So even if the hardware connections are perfect and the generated voltage and currents are correct, a wrong meter constant will produce incorrect measurement results. So it can be entered in secondary or primary values, and it's linked together based on the CT and PT ratio, which is defined already in the device test object. Then we have the CT and PT ratio. So this value represents the primary and secondary ratios for the current transformer and voltage transformer connected to the meter. For example, if the meter is connected through the external CTs and PTs, so the meter module must know these ratios in order to correctly display the primary and secondary quantities. So in this section, these values are displayed only for reference. As you can see, it's grayed out, but the actual CT and PT settings are configured separately in the device setting tab here. Then the setting time. So the setting time defines how long the system waits before beginning the actual measurement after voltage and current are applied to the meter. So the meter may need a short stabilization period before it reaches a steady state operation. If a measurement starts too early, the reading may still be unstable and calculated error may not be accurate. So this setting time helps to avoid any problem by giving the meter enough time to stabilize before pulse counting and calculation begins. Then we have here the pulses per rotation. So the pulses per rotation parameter here defines how many pulses correspond to one complete rotation of the meter disk. So in most practical applications, this value is set to 1 because most of the rotating disk meters generate 1 pulse per full rotation. So this parameter becomes important during the creep testing and the rotational movement evaluation. Then we have the meter class. As you can see, it's 0.5 here. So we have to define the meter class. The meter class representing the expected accuracy level of the meter according to standards and manufacturer specs. So the meter module uses this value as the default tolerance during test evaluation. So in other words, the software compares the measured error against the allowed error limits based on the selected meter class, and this helps automatically determine whether the meter passes or fails during the test. So this completes the meter test object section. As we have seen, this settings forms foundation and calculation and evaluation performed later by the meter module. So let us open the meter module itself and navigate through the different parameters.